Round robin RR is like a group of children taking turns on a slide. If one child stays on the slide for a very long time, the others have to wait and may get bored. The same thing happens in a computer. A process that keeps the CPU for a long time blocks other processes, especially interactive ones such as a game or a text editor. RR gives every ready process a small equal slice of CPU time, called a time quantum, before moving to the next process. This simple rule creates a feeling of fairness and keeps the system responsive because each process knows it will get a chance to run soon after it yields the CPU. The time quantum is the length of a single turn. If the quantum is very short, for example 1 millisecond, the scheduler will switch from one process to another many times per second. This makes the system feel very responsive, but the CPU spends a lot of time saving and restoring registers, the context switch overhead, which reduces useful work. If the quantum is very long, for example 200 milliseconds, the behavior becomes almost the same as a first-come first-served queue, because the first process will finish most of its work before anyone else gets a turn, hurting interactive tasks. In practice, operating systems choose a quantum between about 10 milliseconds and 100 milliseconds, often based on the timer tick frequency. For example, 100 Hz gives 10 milliseconds. The chosen value therefore balances three system-level goals: responsiveness, CPU utilization, and fairness. The round-robin algorithm can be described in 4 simple steps. 1. Keep a first-in-first-out ready queue that holds all processes that are ready to run. 2. Remove the first process P from the head of the queue. 3. Run P for at most one time quantum queue or until P finishes, whichever comes first. 4. If P has finished, discard it, otherwise append P to the tail of the queue. 5. Repeat from step 2. A compact pseudocode representation is: ready queue becomes list of all newly arrived processes. Queue becomes time quantum milliseconds. While ready queue not empty do. P becomes ready queue pop front. Runtime becomes minimum of queue and P remaining time. CPU run P runtime. P remaining time becomes P remaining time minus runtime. If P remaining time greater than 0, then ready queue pushback P not finished go to back. Thels record completion P. Zend while the loop continues until every process has completed. Performance of any scheduling algorithm is measured with several numbers. Throughput, how many processes finish per unit of time, for example 5 processes per second. Higher throughput means the system gets more work done. Turnaround time, the total time a process spends in the system from arrival to completion. Turnaround equals completion time minus arrival time. Waiting time, the time a process spends in the ready queue not running. Waiting equals turnaround minus CPU burst. Context switch overhead, the extra CPU cycles needed to save the state of the current process and load the state of the next one. If each switch costs C milliseconds and the scheduler performs S switches, the lost time is C times S. In round robin, the number of switches is roughly total CPU time divided by Q, so a smaller quantum raises the overhead. These metrics let us compare round robin with other policies and see the trade-off between responsiveness and raw efficiency. Consider 3 processes that arrive at time 0. P1 needs 10 milliseconds of CPU time. P2 needs 5 milliseconds. P3 needs 8 milliseconds. Choose a quantum queue equals 4 milliseconds. The round-robin order showing only the start of each slice is 0 to 4 P1 remaining 6. 4 to 8 P2 remaining 1. 8 to 12 P3 remaining 4. 12 to 16 P1 remaining 2. 16 to 17 P2 finishes. 17 to 21 P3 remaining 0. Runs 4 milliseconds, then 0 milliseconds left. 21 to 23 P1 finishes. Completion times: P1 equals 23 milliseconds, P2 equals 17 milliseconds, P3 equals 21 milliseconds. Turnaround times: P1 23, P2 17, P3 21. Waiting times: P1 23 minus 10 equals 13, P2 17 minus 5 equals 12, P3 21 minus 8 equals 13. Average waiting time equals open parenthesis 13 plus 12 plus 13 close parenthesis, divided by 3 equals 12.67 milliseconds. If we used first in first out order P1-P2-P3, the waiting times would be 0, 10, 15, average 8.33 milliseconds, which is smaller, showing first in first out can be better for pure CPU-bound work. However, with a short quantum, the system stays responsive because no process runs longer than 4 milliseconds without giving others a chance. Policy: how it picks the next process. Typical average waiting time example: fairness. FIFO, first process that arrived, 8.33 milliseconds. See example, low, a long job can block later jobs. SJF, shortest remaining CPU burst, 5.00 milliseconds. If we could reorder to P2-P3-P1, low, long jobs may starve. Priority, highest priority number depends on priority levels. Low priority may wait long, medium, high priority jobs dominate. RR, round robin with quantum Q, 12.67 milliseconds. Example, high, every ready process gets an equal turn. The table shows that RR sacrifices the smallest average waiting time to obtain fairness and good response for interactive tasks. FIFO and SJF can be optimal for batch workloads, but can cause a single heavy process to dominate the CPU, hurting responsiveness. Modern kernels still use the RR idea, but they add refinements. In Linux, the completely fair scheduler, CFS, keeps a virtual runtime for each task and always runs the task with the smallest virtual runtime. This approximates RR while allowing tasks to run for a variable amount of time based on their weight. For true real-time classes, SCHED_RR, Linux enforces a fixed quantum that can be tuned with /proc/sys/kernel/sched RR timeslist.ms. Windows uses a per priority quantum, around 20 milliseconds for foreground apps, and a round-robin pass among threads of the same priority level. Administrators can change the quantum via system registry or systel on Unix-like systems. Tuning guidelines: a smaller quantum improves latency for UI-heavy programs, while a larger quantum helps CPU-bound compute jobs by reducing context switch cost. I/O-bound processes spend most of their time waiting for disk, network, or user input. When they are ready to run, they usually need only a tiny burst of CPU, often far less than a typical quantum. In RR, they take a slice, finish their short work, then block again, allowing the scheduler to give the next process a turn. This natural behavior keeps the system interactive. The UI thread gets frequent turns, while the I/O threads quickly return to waiting state. CPU-bound processes, on the other hand, need many quanta before they finish. They will keep re-entering the ready queue after each quantum, paying the context switch cost each time. If the quantum is too small, the CPU spends a noticeable fraction of time just switching, which hurts overall throughput. Therefore, system designers often pick a quantum that is long enough for the average CPU-bound slice, but short enough that an I/O-bound slice still fits comfortably inside one quantum. RR guarantees no starvation because every ready process will eventually be placed at the tail of the queue and will be selected again. However, RR does not guarantee perfect fairness when processes have very different CPU needs. A long CPU-bound job may still finish much later than a short job, and the overhead of many context switches can penalize all jobs. To improve fairness and reduce overhead, modern systems use several tricks. Dynamic quantum adjust queue based on recent CPU usage. Short-running tasks get a smaller quantum, long-running tasks a larger one. Multi-level feedback QMLF queue processes start in a high-priority round-robin queue with a small quantum. If they consume the whole quantum, they are moved to a lower priority queue with a larger quantum. This separates short interactive jobs from long compute jobs. Aging gradually increase the priority of waiting processes so that they will eventually be selected, preventing indefinite postponement. Even with these enhancements, RR is still a simple, robust baseline that works well for general-purpose operating systems, where fairness and responsiveness are more important than the absolute minimum average waiting time.